Module 7 covers roots and radicals. Those terms are used interchangeably, as well as root functions, working with radical equations, working with complex numbers, and it's a nice reprieve from how tough Module 6 was. So make sure you're completing your guided notes as we go along. Again, this is Module 7, Part 1, where we're going to talk about an introduction to radicals and their graphs. So previously in Module 4, we studied exponents, which is what we use to square a number or even cube a number. So for instance, 3 squared is 9. And if I took -2 cubed, my pencil would work. That would be lovely. 2 cubed, that would be -8. For instance. There we go, now my pencil's working. And next what we're going to do is study square roots or higher degree roots. We also call these radicals. And that's what we do, is they take us from a square of a number back to the number itself. So since 3 squared is 9, the square root of 9 is 3, I could also take the cube root of -8, and that would give us -2. Roots undo exponents is a good way to think about this. So for instance, if I was taking the nth root of a number a and I got out b, that would mean that b to that nth power would give me a as well. So it's important to note that a and b are of the same sign, and n is a natural number. We call that our index. For square roots, I won't typically write the index like I did here in a. It's typically just omitted. So if I wanted to find the square root of 36, that'd be 6, because 6 squared is 36. If I wanted to take the cube root of 3, cube root of 27, that would be 3, because 3 cubed is 27. If I take the cube root of -27, that's -3, because -3 cubed is -27, and so forth. So let's practice simplifying some radicals. The square root of 64 is 8, and yes, you can use your calculator for these, but when it comes to simplifying radicals in later sections, your calculator is not going to be helpful. So this is really good practice. The cube root of 64 is 4. Next, I've got the square root of 5 over 125. Well, that fraction already, I know I need to simplify that. That gives me the square root of 1 over 25. And an important note is, much like exponents, roots distribute over division. So that would give me the square root of 1 over the square root of 25. Well, the square root of 1 is 1, the square root of 25 is 5, so that's how that would simplify. The cube root of 125, that is going to be 5, because 5 cubed is 125. The fourth root of 16 is 2, because 2 to the fourth power is 16, right? We can take higher powers than fourth, right? I could take the fifth root of 32. And that would be 2, because 2 to the 5th is 32, right? We can take these higher degrees roots. The cube root of 8 over 27, well, that's going to be the cube root of 8 over the cube root of 27. And that'll give me 2/3, right? So we're just practicing undoing exponents. We're practicing taking the roots. So there's a few different cases when it comes to taking nth root. So if n is even and a is positive, we say n root a is the principal nth root of a. Basically, I know I could take 2 squared to get 4 and -2 squared to get 4, but when I want the square root of 4, when I write that, I only ever want a 2 back out. If I want the negative root, I'm going to put a negative in front of that root. So -4. Negative root 4 would be -2. Our second case is if n is even and a is a negative number, we cannot take a root. This is going to be a complex number. And the reason for that is, if I wanted the square root of, say, -4, that would mean, okay, what are 2 things that I can multiply together in order to get -4? Well, there's no two things that are the same thing. Both of these have to be identical, because if I had two positives, that wouldn't give me a negative. If I had one negative, that would give me a negative, but we need both of these to be the same. And if I had two negatives, that would give me a positive. So this is a complex number. Wait around till this we're going to see at the end of this module. And case 3 is if n is odd, then there's exactly one real root. And I can take the odd roots of negative numbers, because let's say I wanted the cube root of -8. That's saying, okay, what can I multiply by itself 3 times to get -8? And that's going to be -2, because 2 negatives make a positive, but one more negative gives us a negative as well, right? So as long as my root that I'm taking is odd, I can take the odd root of a negative number. I could even do an odd higher degree root, like a 5th root. So something to keep in mind. So if I want the square root of 100, that's 10. If I want negative square root of 100, that's -10. If I want the 4th root of 81, that's going to be 3. If I want the negative 4th root of 81, that's going to be -3. And if I want the 4th root of -81, because this is even, this is going to be possibly a complex number, so we can't take the root. Right now, it does not exist. Another thing you could write is not real. That'd be another way to put it. But I can take a cube root of a negative. My ideas for coming up with examples are so creative, you guys. And then the cube root of 8 would be 2. So those are some cases of how to take roots. We're going to learn more how to simplify roots later on in this module, multiply them, add them and subtract them, lots of fun operations. But the first thing I want us to do is kind of learn how to visualize what the graphs of these functions would look like. So if I have a function, f of x, it's a function because it passes the vertical line test. Let's say f of x is the square root of x. So I want to pick some values to substitute in that would make perfect square roots. And the first few perfect square roots are 0, 1, 4, and -9. And what the square root function does is it pairs each number with its principal square root. So if I substitute in 0, I get the square root of 0, which is 0. If I substitute in 1, I get the square root of 1, which is 1. When I substitute in 4, that's like taking the square root of 4, which is 2. And if I substitute in 9, I get the square root of 9, which is 3. So it's going to look like this. And we notice that it has a restricted domain and range. Before, when we were working with linear equations, as long as they had positive, negative, or 0 slope, right, their domain was all real numbers. Now, I can't have anything in my domain be negative, because remember, let's say I wanted to take the square root of -1, if x was -1. This does not exist. This is complex. This is not a real number. I can't graph it on our real number line that we have here. So the graph of the square root of x will look like this. And when I say it's continuous over its entire domain, what I mean is that I can draw it without picking up my pencil. That's as deep of a definition of continuous as we need right now. We could also have the cube root function. This pairs each real root with its cube root. So I want to pick nice values for x that would give me perfect cubes. So the cube root of -8 is -2. The cube root of -1 is -1. The cube root of 0 is 0. The cube root of 1 is 1. And the cube root of 8 is 2, right? And this has the domain and range we've seen before, right? Our domain is all real numbers because I can take the cube root of a negative. And it is also continuous over its domain because I can draw it without picking up my pencil. And rational functions were not continuous over their domain because I'd have to pick up my pencil in order to draw, a rational function. So we've seen some that were discontinuous or not continuous before. So when I'm thinking of graphing these, I can think of them as, I can think about vertical shifts of my functions. So if I have a function f of x and I add some constant, it's going to have the same shape as the graph of f of x, but it's shifted k units along our y-axis vertically. And we can kind of do a throwback, real quick throwback, to when we were working with linear functions. So let's say I have the line y equals x, right? That's going to be a line that looks like this. My y-intercept is 0. And if I wanted to say what's y equals x minus 2, well, now my y-intercept is -2. So my graph has been shifted down, but it's going to have the exact same shape, right? It's going to have the exact same slope. I tried to draw a straight line, guys. It didn't work well. I could also shift that graph up. I could have y as x plus 3. So it has the same slope, but now I've got a y-intercept of 3, right? So when I take a function and I add a constant to it, that's going to shift my graph up and down. The same is true for radical functions. So here in red, I have the square root of x, and I could subtract or add a constant, and that's going to shift my graph up or down. Note that this doesn't change my domain. My domain is still from 0 to infinity. But what changes is my range, right? Now, as opposed to having a range from 0 to infinity, this green graph right here has a range from -2, because it looks like it was shifted down 2, make that a 2, to positive infinity. And this blue graph has a range of 2 to infinity. So when we shift our graphs up and down, what we're doing is we're changing our range. Our domain is not affected. So let's practice graphing a few of these radical functions. So for our first example, what we're going to do is we're going to graph this radical equation. We're going to describe the shift and state the domain or range. So the first thing we need to do for every problem is choose x values. And we want to do that by setting our radicand. That's what's under the radical, if I didn't mention that already. Our radicand equal to some perfect squares or cubes, depending upon what degree radical we're taking. So this is a square root. So I want to pick the first few perfect squares. So I want x to be 2. Nope, I want x to be 0, x to be 1, and x to be 4. So those are going to be our first few perfect squares. So I'm going to substitute these in to my function. So I'm going to have f of 0 is the square root of 0 plus 2, which is 2. I'm going to have f of 1, which is the square root of 1 plus 2, which is 1 plus 2, which is 3. And I'm going to have f of 4, which is the square root of 4 plus 2, which is 2 plus 2, which is 4. And I didn't need to add those parentheses there, I just did. So now I've got 3 points I can go ahead and plot. And typically for a square root or a cube root, you're going to want at least 3 points. So I go to when x is 0, y is 2. When x is 1, y is 3. And when x is 4, 2, 3, 4, y is 4. And I connect those points. So this graph has been, if I wanted to describe the shift, this graph has been shifted up to, my domain goes from 0 to infinity, and my range goes from positive 2 all the way to positive infinity. For our second example, I'm going to look for the cube root of x minus 3. So I need to pick the first few perfect cube roots. So I know the first few perfect cubes in this case are when x is -1, x is 0, and x is 1. All right, let's substitute them in. I have f of -1 is the cube root of -1 minus 3. That's going to be -1 minus 3, which is -4. I'm going to have f of 0, which is the cube root of 0 minus 3, which would be 0 minus 3, which is -3. And I could fill in my table if I want. Then I've got f of 1, which is the cube root of 1 minus 3. So 1 minus 3, which is -2. And I can go ahead and plot these points. Okay, so when x is -1, y is -4. And 2, 3, 4. I also have when x is 0, y is -3. And when x is 1, y is -2. Now, these look to be in a straight line, but we need to remember that we're taking a cube root, and it is going to have a shape like this, always. If I wanted to, I could find a couple more values. The next few perfect cube roots would have been 8 and -8, but it's going to look like this. So I could describe this as it has been shifted down 3, and my domain and range are both all real numbers. So I can shift my graphs up and down by adding to our function, but I can shift my graph left and right by subtracting from our function, from what's under the radical. And one thing we have to notice is that it's a little opposite, and we'll see why that is as we graph a few examples. So for example, if I wanted the square root of x minus 2, this graph has been shifted right 2. Even though we're subtracting, it's shifted right 2. If I've got the square root of x plus 2, that's going to be shifted left 2. And the reason it's shifted opposite is because what would make this the square root of 0, right? Because here I've got 0, 0. Well, that would be when x is -2. So the -2 plus 2 would be 0, right? So it's opposite. That's why this one was shifted left. The same thing would be true for the one that's shifted to the right. If I have y equals the square root of x minus 2, what would I need to substitute in for x to make that 0? Well, that would be a positive 2. So when x is positive 2, that's why y is 0. So first thing we need to do is choose find 3 y values, and we need to do that by finding our x values. And how I find the x values that I need to use in order to make our answers come out as perfect squares is by setting this x minus 3 equal to perfect squares. I wouldn't just want to pick 0, 1, and 4 like I had before, because if I substitute in 0, well, that's going to give me the square root of -3. If I substitute in 1, that's going to give me the square root of -4. That's not going to work well. So let's go ahead and set x minus 3 equal to the first few perfect squares, which are going to be 0, 1, and 4, always. And when I solve these for x, I see x is 3, x is 4, and x is 7. Those are going to give me values that when I substitute in to my function, give me perfect square roots as answers. So they're so much easier for us to graph. So if I find the f of 3, that's the square root of 3 minus 3. So f of 3 is the square root of 0, which is just 0. Nice. If I've got f of 4, that's going to be the square root of 4 minus 1. So f of 4 is the square root, I messed up, 4 minus 3, which is the square root of 1. So f of 4 is 1. Sometimes I'm thinking too far in advance. And if I take x to be 7, I have f of 7 is the square root of 7 minus 3. So f of 7 is the square root of 4, which is 2. So now I have 3 really nice, easy to graph ordered pairs. So I know when x is 3, y is 0. When x is 4, y is 1. And when x is 7, up just barely on my graph, y is 2. This graph has been shifted right 3. When we're subtracting 3 from under a radical, that's shifted my graph right 3. My domain has now shifted. My domain is no longer starting at 0. My domain starts at 3 to positive infinity. And my range, because I shifted it left and right, my range didn't change. My range is going to be from 0 to positive infinity. So when we're graphing a radical, we find at least 3 y values. We need to make sure those y values, to make our lives easier, give us nice square roots that we can graph as nice, even, whole integers. And then we state our domain and range, always describe the shift. That's a good practice to get into. And we're going to do the same thing when we get to quadratics in Module 8. So here's kind of a summary of all the shifts, right? If I add a positive when k is greater than 0, this is going to shift my graph up. If I subtract, so I add a number that's less than 0, that's going to shift my graph down. If I add, that's going to shift it to the left. If I subtract, that's going to shift my graph to the right. And if you want to, you can explore this interactive graph shift example on Desmos. So let's graph the following and describe the shift. So I'm going to look at this and I'm going to say, okay, it's got a minus 1 on the outside. That's going to shift my graph down 1. And this plus 4 on the inside, that's going to shift my graph to the left 4. So let's make sure that that is the case. I could still graph this by setting what's under the radical equal to the first few perfect squares. Another way I could graph this is by taking my regular square root function. So that would be this. And I need to shift it down 1 and left 4. So every single point, I could shift down 1 and left 4. I could take this point and go down 1, left 4, down 1, left 4, down 1, left 4. And this is going to be my new graph. Well, how did I know that? Let's find the points and see if it's true. So I need to solve this for when x is negative 4, x is negative 3, and x is 0. If I want f of negative 4, that's the square root of negative 4 plus 4 minus 1. So that's the square root of 0 minus 1. So 0 minus 1 is negative 1. So when x is negative 4, y is negative 1. Oh, look at that. If I want f of negative 3, that's the square root of negative 3 plus 4 minus 1. That'd be the square root of 1 minus 1. 1 minus 1 is 0. Well, would you look at that? When x is 3, negative 3, y is 0. And for 0, I want f of 0, which is the square root of 0 plus 4 minus 1. That's the square root of 4 minus 1. That's 2 minus 1, which is 1. So when x is 0, y is 1, right? I can look at my graph and see how it shifted from the original, or I can go ahead and find 3 points on my graph. It's totally up to you. There's multiple ways to solve every problem. There are multiple ways to graph. One is by finding the points. Another is by looking at the shift of the parent function. In this case, we could call f of x equals square root of x our parent function or our original function that we've altered. Last example, this time we're taking the cube root. This has been shifted up 4 and right 2. So I can find the first few points by setting this equal to the first few perfect cubes, right? The reason I'm setting x minus 2 equal to -1, 0, and 1 is because those are perfect cubes. So I'd have x is 1, 2, and 3. That's going to give me 1, 2, 3 to plug into my function. F of 1 would be the cube root of 1 minus 2 plus 4. That's the cube root of -1 plus 4. -1 plus 4 is 3. So when x is 1, y is 3. When f of 2, that's the cube root of 2 minus 2 plus 4, which is the cube root of 0 plus 4, which will just give me 4. And then for 3, I've got f of 3 is the cube root of 3 minus 2 plus 4, which is the cube root of 1 plus 4. 1 plus 4 is 5, right? So this is going to be my new function. I know it looks something like this. And we could think of this as our original function. So here's our original cube root function. Shifted right 2 and up 4. See this point here? I'm going to shift it right 2, up 4, right 2, up 4, right 2, up 4. So you get to decide how you want to graph these, be it by finding those ordered pairs or by graphing the shift. I find it easier to graph the shift because this is a cube root function. My domain is all real numbers and my range is also all real numbers.